grades on Canvas. The way those grades are set up is you have two columns. One column is the multiple choice score, and that's in points. And the other column is the fill-in-the-blank score, and that's also in points. If you add those two numbers together, that's your grade score. So for example, if you had a 62 on the multiple choice and you had a 20 on the fill-in-the-blank, you have an 82. So you're in the B range. Now, Canvas doesn't deal with points. It always deals with percentages, and that makes things a little more complicated. Now, the multiple choice score that you see has had 12 points added, because when we calculated the average of the fill-in-the-blank, that came out to, I think, 15.7. And the average on the multiple choice was in the neighborhood of the mid-40s. So you add those two together, and I think the mean was like a 59. So added 12 to that to bring the mean for the class up to a 71 or 72. So that's where the mean for the class is. The way those scores were done, again, is on the multiple choice. That was out of 100, but the score you see has had 12 added. The fill-in-the-blank was out of a total of 20, even though there were 29 blanks. So if you may see a score of, say, 27, which means you got 27 of the 29 blanks right. And if you have a 15, it means you got 15 out of the 29 blanks right, but you really effectively have a score of 15 out of 20. So there's a lot of extra bonus points built into those fill-in-the-blank questions. So what we're going to do today is I'm going to pick up where we left off last time. I just wanted to finish the story of oligodendrocytes and multiple sclerosis. It has really important clinical implications for many of us. Almost all of us know someone with multiple sclerosis. I just wanted to spend a little time talking about how the oligodendrocytes are involved in this disease. And it also points out what we talked about last time, that many of the diseases of the nervous system, which are expressed as neuronal diseases, which appear to be neuronal dysfunction, are in fact problems of the glia. And I suspect as time goes on, we're going to find more and more and more of these diseases which have been ascribed to neuronal problems, which are in fact dysfunction in the glia. And this is a good example of that. Then the most of the time I want to spend here is talking about the physiology of excitable cells. And this topic that we're going to talk about today on the physiology of excitable cells lies at the heart of understanding the electrical gradients, electrical signals that we have in the nervous system. So this is fundamental to understanding of signaling in the nervous system. We're going to lay this out as the idea of generating a membrane potential, but that's just a term which describes generating a potassium battery. And we're going to use the separation of potassium across the phospholipid bilayer to store energy for all other forms of signaling. So what we want to think about here initially is how do we separate potassium across a membrane in such a way that we can generate a battery that has potential energy that can do work. We're going to lay this out initially with three simple propositions. There's going to be a phospholipid bilayer. It's virtually impermeable to ions. But there are pathways across the phospholipid bilayer, particularly for potassium. And these are going to be potassium channels. We're going to see that the potassium channels or leak channels are open all the time. And so now, because we have potassium leak channels that are open, the membrane is permeable to potassium. So at rest, the predominant permeability will be for potassium ions, and that's because we have open potassium channels. But if all we had were potassium ions on the outside and potassium ions on the inside and permeable channels, the system would come to equilibrium, so we had concentrations equivalent on the outside and the inside. But that doesn't happen. And the reason it doesn't happen is that on the inside of the cell, there are these what we call large negative anions. These are ions that don't cross the phospholipid bilayer. These are ions, usually they are organic acids, sometimes they're proteins, but they're these great big negatively charged molecules. Then what we have to think about is the idea that we have these negatively charged ions on the inside that don't move, along with potassium ions. So now we're going to get an electromagnetic interaction between these two. Effectively, the large negative ions are going to prevent the potassium ions from moving. the potassium ions will start going down their concentration gradient through the potassium channels. The membrane is permeable to potassium. But a new equilibrium is reached pretty quickly because as the potassium leave, they're suddenly stopped by the large negative anions. So we've reached an equilibrium. So the three things that we're going to talk about initially to generate a potassium equilibrium are the potassium selective ion channels, the large negative anions, and the potassium ions. We'll set this up initially. That's going to generate a membrane potential. Conceptually, this is what I want you to see. But for those of you who like numbers, I'm going to walk through something known as the Nernst potential. Because by using the Nernst potential, and I'll try to simplify this way down, but the Nernst potential provides a means whereby we can describe the disparity in concentration of ions across the membrane and yield from that an electrical term, a voltage. So we're going to see that we'll have a voltage as potential energy stored across the membrane, related mostly to the potassium concentration on the outside or the potassium concentration on the inside. But the Nernst potential includes some other characteristics. These were all derived from Boltzmann equations. They were all derived from an understanding of the statistical mechanics of ions moving through a channel. But in fact, we don't have to go through all of that. We can simply say that we know there's a constant here. R stands for the gas constant, that's a constant number. T is the temperature, that'll vary with whatever the degrees Kelvin is, but it won't be that much different, whether it's 37 degrees centigrade, add that to minus 272, or whether it's room temperature at 28 degrees centigrade. These numbers are going to be fairly fixed. Z is the charge on the ion, F is the Faraday, that's a constant. So this number comes out pretty much as a constant. Then what we need to look at is the natural log of potassium concentration outside or inside. Well, we're going to convert this to the log base 10, multiply it by 2.72. That now will leave the equilibrium potential equal to a constant number times the log base 10 of the concentration outside of the concentration inside. We'll work through that, simply to show that we're now with more potassium on the inside than the outside, we're going to get a negative number here. That will give us a negative potential. All of that will be done using the permeability based on the potassium leak channels. But those in normal biological membranes are not the only channels. We're going to have a whole series of different channels. And the first one we're going to talk about is a sodium selective channel. So again, we're going to run through a kind of thought experiment. So we'll put more potassium on the inside than the outside. That will generate the membrane potential. But then we're going to put more sodium in the outside than the inside. Just as we saw an equilibrium potential for potassium, as long as there was permeability for potassium across the membrane, we again can find an equilibrium potential for sodium, assuming there's a permeability across the membrane. Now initially, we're going to simplify this whole lot. Initially, we're going to say these sodium selective channels are all closed. Say there are none of them open. And then we're suddenly going to open them. And that's going to bring us to this mantra. And this is a really useful mantra. And if you could take another neurobiology course, you'll quantify this in something called the Goldman equation. But for our purposes here, we can simply say the membrane potential seeks the equilibrium potential of the ion whose permeability is dominant. So we'll initially walk through this mantra describing a membrane where the dominant permeability is to potassium. So that means the membrane potential is going to be close to the equilibrium potential for potassium because that's the dominant permeability. But now if we magically think about how we can switch things and suddenly open up 1,000 times more sodium selective channels than we have potassium selective channels, then the permeability immediately switches from being predominantly potassium to being predominantly sodium. So now we have switched the permeability, and if we follow the mantra, the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. Now the membrane potential is going to go up to the equilibrium potential for sodium. So we've switched the polarity on the membrane. That's all well and good. we go from, say, in biology, from about minus 70 to plus 40. But then how do you come back down again? And what we'll see is that these channels, these sodium selective channels, not only have the ability to open very rapidly, but they also have the ability to close very rapidly. So they're like little valves. And so when they open, the dominant permeability is to sodium. But when they close, because we continue to have potassium weak channels, the dominant permeability then will be to potassium. So we'll bring the membrane potential back down again, and we'll walk our way through that. And then if there's time, we'll talk about the generation of an action potential, where we're now going to invoke a potassium leak channel, a voltage-gated sodium channel to change the permeability really fast, and then a voltage-gated potassium channel to rapidly repolarize the membrane to increase the permeability to potassium. And we'll walk our way through that. But let's start here with I better start here with oligodendrocytes. And multiple sclerosis. What happens in multiple sclerosis is a disease where the immune system put this in quotes, breaks into the central nervous system. We don't know why this happens. We don't know why some people are more susceptible to it than others. We don't know why this seems to happen almost exclusively in northern latitudes, and if you live in tropical latitudes, it doesn't happen. There's a lot we don't understand. What we do understand is that when the immune system breaks into the central nervous system, it generates antibodies and T killer cells that attack the myelin basic protein. In myelin. Well, when the antibodies attack the myelin basic protein in the myelin, it basically destroys the myelin sheath around the axon. And you'll remember from last time, we said that we had that important arrangement where we had the myelin sheaths forming the insulating layer. And when the myelin sheaths are attacked by the immune system, we basically demyelinate the axon. So we lose that insulating layer, and we lose the capacity to conduct action potentials in these axons. So when the immune system attacks the myelin, we demyelinate axons and thereby impair electrical signaling. Specifically, we are impairing electrical signaling in the conductal regions. So this disease manifests itself as a problem with the nervous system. It manifests itself as an inability to conduct action potentials in certain parts of the brain. And if you do MRIs of individuals with these diseases, you can see where the demyelination has occurred in particular spots. What commonly happens with individuals with this disease is they tend to have what they call relapses. It's called relapsing and remitting form of the disease. It means that you'll go for periods of weeks, months, maybe even years where you're not affected by the disease. Something happens, the immune system gets geared up, it goes in and attacks the myelin basic protein, and you again have an attack. Now, these oligodendrocytes have the capacity to rewrap around the axon. They can rewrap around the axon several times. So you can undergo a demyelinating event, but then these oligodendrocytes will remyelinate. The trouble is every time they go through that process, they don't do quite as good a job as they did the last time. So it tends to be a degenerative disease. So the treatment of the disease right now is to try to prevent each of these bouts of the attack of the immune system. And if you can hold those attacks at bay for as long as possible, the prognosis is pretty good. If these relapses occur, if the remitting part of the disease where you get the activity of the immune system against the oligodendrocytes, the more frequently that happens, the worse the prognosis. So we're trying to stretch out the intervals between the attacks as long as possible. Having said that, I think I'm pretty optimistic that we're going to see remarkable changes in this disease in the next few years. And the reason I say that is we're coming to a better and better understanding of the immune system. And now, if you watch TV, you'll recognize there are drugs which are used to treat rheumatoid arthritis. That's an autoimmune disease. There are drugs to treat psoriasis. That's an autoimmune disease. There are drugs to treat the psoriatic arthritis, which is an autoimmune disease, and even autoimmune diseases that affect the intestines, such as Crohn's disease. We're beginning to get a handle on how to treat those diseases by using antibodies to block certain aspects of the immune system. I feel pretty confident it's only time before we get this one sorted out too. It's going to be a boon to many, many people. So any questions on that? Well, with that, let's move on and begin the topic that we really need to spend some time on here today, which is the idea of the physiology of excitable cells. And when we think about the physiology of excitable cells, we think about neurons, we think about muscle, and what we're going to talk about today of generating a membrane potential and initiating the concepts of electrical signaling across phospholipid bilayers. As we do this, recognize this is going to be foundational for all of the signaling mechanisms in the central and peripheral nervous system, as well as muscle. So we'll start here simply with the generalized label of physiology of excitable cells. We're going to start here by generating a resting membrane potential. The resting membrane potential is nothing more than a potassium battery generated by separating potassium ions across phospholipid bilayer. So we'll start here simply by drawing the phospholipid bilayer. We've done this many times. We'll arbitrarily make this outside. We'll make this inside. We're going to put on the outside, we're going to put 10 millimolar potassium ions. And on the inside, for round numbers, we're going to put 100 millimolar potassium ions. Now, the way it's drawn, of course, these ions won't readily move across the phospholipid bilayer. The charged ions of potassium it's not thermodynamically favorable for these charges on potassium to move through the hydrophobic tails. But we've seen earlier that we can provide a pathway across that phospholipid bilayer by simply adding a transmembrane protein. And this transmembrane protein is going to be a potassium selective ion channel. Now, I think that you'll immediately see what the problem is here. If we simply were to say, Out here in the ocean, we have 10 millimolar potassium, and inside the cell, we have 10 times as much. We have 100 millimolar potassium. If that's all we did, and we had a potassium selective ion channel, it wouldn't be very long till the potassium would run down its concentration gradient, and you'd end up with 10 millimolar potassium in the inside and 10 millimolar potassium on the outside. But that doesn't happen. And the reason it doesn't happen is that there's another set of characters in here. On the inside of the cell contains what I'm simply going to label as A negative. And these are large, impermeant anions. The precise species of these anions is variable. Sometimes they are organic acids, sometimes they're proteins. But the major idea is that they're negatively charged and they can't escape. They're stuck inside the cell. But the potassium ions can leave. So the potassium ions, now that we have added these large negative anions, we're 100 millimolar potassium on the inside and 10 on the outside. So potassium starts to run down its concentration gradient. It starts to move from regions of high concentration to low concentration. But then not many ions move. Only a handful of ions move before now the electrostatic charge on the large negative anions takes over. And the positively charged potassium ions are attracted to the large negative anions. So now we have a kind of break. We have a break where as the potassium starts to leave, suddenly those potassium ions are held in check. They're held in place by the large negative anions. At the point where the tendency of the potassium to run down its concentration gradient is exactly balanced by the tendency of the potassium to be held in place by the electrical gradient, is said to equilibrium. You can spell that out. Equilibrium for potassium is reached when the tendency for potassium to leave down its concentration gradient is balanced or equal to the electrical gradient. Let me say that a little differently. To the effect of the electrical gradient holding the potassium ion in place. So we've now reached an equilibrium. So let's try again to get your head around the equilibrium. The equilibrium is such that potassium wants to run down its concentration gradient and have 10 millimolar inside and 10 millimolar outside. But it doesn't take more than a handful of these ions to leave before the effects of the large negative anions are shown. And the large negative anions, because of the negative charge and the opposite charge of potassium, will now put a brake on the movement of the ions down their concentration gradient. And you've reached an equilibrium. We can calculate that equilibrium. I'll do it here. We can calculate the equilibrium from something known as the Nernst potential. The Nernst potential says, it's an equation that says the equilibrium potential for, in this case, potassium, is equal to RT over ZF times the natural log of the potassium concentration on the outside divided by the potassium concentration on the inside. Now, if you take a course in physical chemistry, you get into statistical mechanics, you'll derive all of this from the Boltzmann equations. It has to do with redox potentials and a whole bunch of other things, and Dr. Boltzmann and Dr. Nernst figured all this out. But the long and short of it is, we can calculate a potential across this membrane based on the concentration of potassium on the outside and the inside at equilibrium. So once we have reached the equilibrium that we described conceptually in the upper panel, we can now calculate that equilibrium by plugging in some numbers. In this case, the equilibrium for potassium is equal to RT over ZF times the log of the potassium concentration on the outside over the potassium concentration on the inside. Now, all I've done here is, if you go through the manipulation of this to convert a natural log into a log base 10, you multiply by 2.72. So when you multiply 2.72 times R being the gas constant, temperature being degrees Kelvin, which is absolute temperature, Z being the ionic charge, and F being the Faraday. Now, once you go through all of these machinations, what you end up with is the equilibrium potential for potassium is equal to 58 at room temperature times the log of the concentration of potassium in the outside, which in our thought experiment here, we set up as 10 millimolar. And the concentration in the inside, which in our thought experiment, we set up as 100 millimolar. This means this is the log of 0.1. The log of 0.1 is minus 1. That means the equilibrium potential for potassium is minus 58 millivolts. That's just to walk us through the numbers. Now, I've simplified this simply by using convenient numbers where the concentration on the outside is 10 millimolar, the concentration on the inside is 100 millimolar. In biology, the number is a little different. In biology, the concentration of potassium here is in terms of 4 to 5 millimolar. And the concentration of potassium in the inside, rather than 100, is 110 millimolar. If you plug those numbers into the Nernst equation, you come out with a number that's in the neighborhood of about minus 70 millivolts. So the resting membrane potential for a typical neuron is in the neighborhood of about minus 70 millivolts. And that resting membrane potential is derived from this peculiarity that we have only potassium leak channels. Potassium moves down its gradient, its chemical gradient, but then shortly thereafter is held in check by the large negative anions. And at that point, we have a surplus of negative ions on the inside. And we can take a measurement of that and say this is a neighborhood in biology of about minus 70 millivolts. So any questions about how we got there? Yes?
In the equation, I understand that you're supposed to multiply by like 2.72 or whatever, but what did you do to the second equation to represent that change?
So all I did in the second equation to represent the change from natural log to log base 10 is I amalgamated all these values. I took into account the temperature in degrees Kelvin, the number for the gas constant, the number for the Faraday, and the number for the charge on the ion. And said those are all constants. Multiplied that by 2.72. That comes up to 58. This number will be a little bit different depending on whether or not you're at room temperature or something a little warmer. So you'll vary a little bit. So this is done at, I think it's 28 degrees centigrade, and commonly for humans, you'll use 37. But numbers may don't change that much. The point to be made is that once we go through all this fancy rigmarole of dealing with these numbers, that what we're really dealing with is the log of the ratio of potassium outside and the inside. And again, I simplified that to make this 0.1, just to make it simple. But you can put, if you're good with logs, you can change those numbers. Yes? No. So question here is about, I hate to use the word wants. Is equilibrium a good thing or bad thing? Well, all of biology is setting up an equilibrium and then using that equilibrium as a form of energy to do something. All of biology is fighting against entropy. That's what we do to stay alive. And the entropy of the situation is not to have any potential at all. And I've laid this out in a kind of magical way to show that you have a disparity of potassium across the membrane. In biology, that disparity will be set up and maintained by the sodium-potassium pump, but I don't want to mention that yet, because as soon as I mention the sodium-potassium pump, students come to think about concentrations. And it's true we have a concentration here, but in a moment we're going to see we can switch this polarity across the membrane enormously without affecting the concentration hardly at all. So I want you to think in terms of these equilibrium potentials and the ions that are involved rather than their real concentrations. Just think about the ratios setting up an electrical potential, and we'll come back to the concentrations later. Yes?
Are we going to have to know how to calculate that, or should we just know the negative?
So the question is, you're going to have to know how to calculate this. I'm not going to ask you to calculate these numbers in this class. If you take a neurobiology class, cellular neurobiology class, you'll work through those calculations. And you'll, in fact, work through these calculations for any number of ions. What I do want you to hold on to, though, is the importance of this log function. And in the case of potassium, one of the things I want you to know about, particularly when we start talking about the nervous system and muscle, is that if you start fiddling with this number of the potassium concentration on the outside, because it's a log function, you don't have to change this number very much, and you change this number by a lot. And what it means is that there are pathologic conditions in humans, but a good example is in elderly cats. In elderly cats, what commonly happens, and cats frequently meet their demise because the potassium concentrations in the plasma start creeping up and up and up. They go into kidney failure, and they can't clear potassium properly. And the potassium concentrations start to go up, and you don't have to change this outside number very much, and you start to polarizing the membrane potential for essential cells in the heart and in the nervous system. So what I want you to know is how important it is to maintain this log value of 10 to 100 or 4 to 110. That log value is the important idea, and how the log function means small changes here make big changes here. That's what I want you to see. Anything else? So what we've done so far is we've set this pattern up here using the three characters of potassium ions, large negative anions, and a potassium permeable channel. Now, across this membrane, I'm going to put another character. Across the membrane now, I'm going to put in a green channel. This is going to be a sodium selective channel. And then I'm going to go through and make up some numbers here, but again, I'm going to try to keep it simple so that the sodium concentration on the outside is in the neighborhood of, say, 100 millimolar. And the sodium concentration on the inside is in the neighborhood of 10 millimolar. Well, we can do the same thing as we did above, because each of the ions will have an equilibrium potential. We can plug in the same numbers, which aren't quite biological, but we can say that the equilibrium potential for sodium now, this is ENA, is equal to RT over ZF times the natural log of the sodium concentration on the outside divided by the sodium concentration on the inside. Again, this number is the same. This is going to come out to be 58 times the log, base 10, of the sodium concentration on the outside, which we arbitrarily, for our purposes here, set to 10. And, I'm sorry, set to 100. And on the inside, we set to 10. So we walk through the numbers briefly again. We have 58 times the log of 10. The log of 10 is 1. So now we have a potential plus 58 millivolts. That's not quite right. In biology, it's not quite right. In biology, we have to use different numbers. We have to plug in here about 130 on the outside and here about 10. And if we do this, the number comes in, it comes in a little higher than this. And I won't go through that. But recognize now we have a new equilibrium potential that we can think about. And from the way I've drawn this, you would say, well, we now have a sodium channel here, we have open potassium channels, then the resting potential has got to be someplace between these two. But the caveat for these sodium selected channels is they have a gate. And normally that gate is closed. So even if you have 100 channels out here, or 1,000 channels, with that gate being closed, what does that say about the permeability of the membrane to sodium if all those channels are closed? There isn't any. Excuse me. So there's no sodium permeability. Well, that brings us to the mantra. I'll write the mantra down. And the mantra is the membrane potential the membrane potential seeks the equilibrium potential for the permeability, for the ion, whose permeability is dominant. So let's apply that here in these cases. Initially, when we set up the resting membrane potential, we only had potassium ions, we only had potassium leak channels. So the only permeability across the membrane was through the potassium leak channels. So the dominant permeability is to potassium. The membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. That means the membrane potential must be down around the equilibrium potential for potassium, which in biology is in the neighborhood of minus 70 millivolts. And our thought experiment was in the neighborhood of about minus 58 millivolts. It's just that we used different numbers in those cases. But now let's recognize one of the hallmarks of these sodium channels, that those gates don't remain closed all of the time, that those gates are openable. And now let's also recognize that there may be 1,000 times the number of sodium channels as potassium channels. So now let's magically open up all of these sodium channels. There are 1,000 times as many of the sodium channels as potassium channels. What's the dominant permeability once these gates are opened? Sodium. Membrane potential seeks the equilibrium potential of the ion whose permeability is dominant. The membrane potential is going up toward the equilibrium potential for sodium. We can draw this. So this is time, and this is voltage. start out here at, in the neighborhood of minus 70 millivolts. And again, if we used our thought experiment, we could start out at minus 58, but let's use the biological number at minus 70. This is said to be the equilibrium potential of potassium, EK. This is the potassium equilibrium potential. And then at the arrow, right at this arrow, suddenly, in our magic, what we do is we open all of those sodium channels. So suddenly now, all the sodium channels are open. The predominant permeability is to sodium. Now the membrane potential is almost instantaneously going to go up to a neighborhood of about plus 40 millivolts, in the neighborhood of the equilibrium potential for sodium. I think you can see from what we've said so far that if all we did was open those sodium channels to increase the permeability to sodium, then this membrane potential will go up to plus 40. Since there's 1,000 times more permeability to sodium than to potassium, this membrane potential would effectively stay here forever. But there are two characteristics of the sodium channels. These sodium channels, the sodium channels open briefly before closing. Now, because of our understanding of the molecular biology of these channels, we don't say they close. We say they inactivate. It's the term that I'd like you to remember, that the channels inactivate, but fundamentally, this inactivation is the same thing as closing. So, at this point now, let's do it all at one time. It takes a little bit of time, but let's now say at this point, the sodium channels inactivate. If the sodium channels inactivate and they're all suddenly effectively closed, what's the predominant permeability? It's back to potassium. So that means the membrane potential is now going to come back down to the equilibrium potential of potassium. Now it turns out, I want to explain one more thing about these channels before we get to it, but it turns out that if we had to rely completely on the potassium leak channels, that this repolarization event would take seconds to minutes. Way, way too slow for biology. In biology, we find this repolarization can occur in, 1 to 2 milliseconds. So we're going to have to invoke another potassium channel, but let's hold that at bay for a moment. What I want to do in the upper panel is ask the question, what opens these channels? We waved our magic wand and the channels opened. But in biology, there's a mechanism for opening these channels. And even here in the first iteration of this, it's going to be kind of magical. The way to open these channels is to provide positive charge. We'll see a little later that this positive charge normally comes from the opening of neurotransmitter-operated channels in the input region. But for our purposes now, what I want to emphasize is that if we would put some positive charge around this channel, the gate would open. So that one of the hallmarks of these channels, these sodium channels, is that these sodium channels are said to be voltage gated. Another term for this is voltage sensitive. No, let me do it another way. Another term for the voltage gated is to say that they are charge sensitive. So that if we go back to this, we can imagine in some way applying positive charge on the cytoplasmic side of this membrane. That positive charge swings open, say, this gate. When this gate opens, now there are two major forces on the sodium. The sodium is going to come down its concentration gradient, because after all, the concentration on the outside is 130 millimolar and 10 on the inside. So there's a concentration gradient bringing the sodium in. But remember, the inside of this membrane is initially negative. So there's also the attraction of the positive charge on the sodium to the negative charge inside the membrane. So there are two forces. Two forces bring sodium into the cell. One is the concentration gradient. And the second is the electrical gradient. So sodium comes in. When the sodium comes through this channel, it delivers positive charge. Remember, these channels, these gates, are charge sensitive. So what's this channel going to do? It's going to open. It's going to bring more sodium in. It's going to open this channel. If we graph that, it looks a little like this. It'd be hard to see in biology, but because each of those, the number of ions that comes in through each of those channel openings is small. But conceptually, we can redraw this in such a way that we look at individual channel openings. So we'll start with the same parameters. This is voltage in millivolts. This is time. This is the resting membrane potential. We're going to give it a value of minus 70 millivolts. And now we start opening channels. We open a sodium channel, and that brings a little sodium in. Those charge-activated gates start to open. And then another one opens, another one opens. And then suddenly we start seeing the opening of each of the channels increases the probability of the next channel opening. So now we begin to see a cascade of channel openings until finally we reach a point here of about, minus 55 millivolts, a point called threshold. And threshold is where the threshold is defined as the point where sodium influx equals potassium efflux. So you can imagine a situation here where you depolarize a little bit, and then for some reason the potassium permeability increases and you come back down. But you can imagine just as you reach threshold, at this point you're on a teeter-totter, you're on a balance, so that theoretically the least little bit more sodium coming in, sodium influx, opens all of the remaining sodium channels. When that happens, then once you reach threshold, then the membrane potential is going to go to plus 40 millivolts. It will reach the equilibrium potential for sodium, more or less. And then at that point, these sodium channels start to close. They inactivate. And then the membrane potential starts coming back down again. Now, I'm going to invoke one more channel type, and we'll come back to this on Wednesday. And here, at the peak of the action potential, at the peak potential, at equilibrium potential for sodium, the sodium channels close or inactivate. But there are another set of characters here called voltage-gated potassium channels. So once we reach the very top up here at the equilibrium potential for sodium, and the sodium channels start to flicker closed, at that very same time, potassium channels start to open. So now you're not dependent upon the small number of potassium leak channels. You now have a whole new set of potassium channels which now become active and increase by a whole lot the membrane permeability for potassium. And you're back to the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. You're going to drive the membrane potential in a millisecond or so back to the equilibrium potential for sodium or potassium, and you start over.